The water you drink every day hides an enormous secret. A mystery so complex that even the world's smartest scientists haven't been able to fully solve it. A discovery that will completely change the way you see the universe. The water keeping. You alive probably didn't come from Earth. Think about that for a second. That transparent water filling the oceans, flowing in rivers, and making up 70% of your body is a space traveler that may have journeyed vast distances before reaching you. The molecules you use to hydrate yourself might have been born inside stars that exploded billions of years ago. Some scientists believe this water arrived through massive collisions with ancient comets and asteroids, like a cosmic rain that seeded water on our planet. Others say it was always here, trapped in Earth's depths since the time when everything was hot magma and total darkness. But what if the truth is even crazier? Hidden among exploding stars, in the furthest corners of space we'll never be able to visit, in this video, we'll dive into the depths of this extraordinary substance, tracing its journey from the first moments after the Big Bang to the mysterious underground oceans of Neptune's moons, from supernova remnants to microscopic isotopes trapped in zircon crystals. Because understanding how water reached us isn't just scientific curiosity. It might be the key to discovering whether we're a cosmic anomaly or if the entire universe is, at its core, a vast ocean teeming with life waiting to be discovered. Have you ever wondered how something as simple as H2O could hold such profound secrets? The story begins with its fundamental ingredients, hydrogen and oxygen, which had completely different origins in the universal timeline. Hydrogen, the most abundant element in the cosmos, emerged within minutes after the Big Bang. The universe was still superheated plasma during a process called primordial nucleosynthesis. This primordial element spread throughout the nascent space, forming the foundation of everything that would come after. Oxygen, however, took a very different path. Absent in the primitive universe, it only began to exist billions of years later, forged exclusively in the nuclear furnaces of massive stars. These stars, upon depleting their fuel, exploded in cataclysmic events called supernovas, hurling oxygen and other heavy elements across the vacuum of space. Consider the implications of this. Every water molecule touching your body contains one element born in the universe's first breath and another that only emerged when giant stars died in explosions that could engulf entire solar systems. Two completely different origins, separated by billions of years, united in a molecule that now forms part of you. These elements traveled through the cosmos in clouds of stellar dust, were absorbed by forming nebulae, and accumulated in nascent, planetary systems. And when they finally met under ideal conditions, hydrogen and oxygen united to form the most vital molecule in the universe, H2O. This means that, long before Earth even existed as a concept, water was already a cosmic possibility, an inevitable heritage of stellar chaos and order. That's why we detect water throughout the observable universe. We find evidence of it in frozen comets, on distant moons, in the atmospheres of exoplanets, and even in vast interstellar clouds floating between stellar systems. There's something almost poetic in knowing that the substance keeping us alive was born from the explosive death of ancient stars, isn't there? And this leads us to an even more disturbing question. If water is so widespread in the cosmos, could life be too? But before we search for alien civilizations, we need to understand how this traveling water is distributed, starting with our own solar system. Think our blue planet holds the monopoly on water in the solar system? The reality is far more fascinating. Some of the most impressive water reserves aren't here, but hidden beneath the frozen surfaces of distant moons orbiting giant planets. Europa, one of Jupiter's moons, conceals beneath its icy crust a liquid ocean containing approximately twice as much water as all Earth's oceans combined. Enceladus, Saturn's satellite, expels geysers of salt water through cracks in its icy surface, captured in spectacular images by the Cassini probe. Ganymede, the solar system's largest moon, harbors more water than Earth itself. And we're not talking about speculative theories. These are facts confirmed by multiple space missions, as if the universe were gradually revealing its aquatic secrets. And as we approach Neptune, things get even more extraordinary. On this ice giant, water doesn't exist only in the conventional states we know. Scientists have identified at least 20 different forms of ice, each with unique properties that challenge our terrestrial understanding. One of these exotic forms is superionic ice, a structure where oxygen atoms form a rigid crystalline lattice, while hydrogen protons flow freely like a liquid, allowing the ice to conduct electricity like a metal. A form of water that doesn't even look like water, existing at pressures 1.5 million times greater than Earth's atmosphere and temperatures rivaling the Sun's surface. And if we expand our search beyond Neptune, to the frozen frontiers of the solar system, there we find the Kuiper Belt, and, much farther away, the mysterious Oort cloud, true cosmic reservoirs populated by trillions of comets carrying primordial ice. Some of these objects travel silently for billions of years in enormous orbits, until gravitational disturbances hurl them toward the inner solar system, where they eventually collide with planets and possibly deliver water. There's an intriguing hypothesis that much of Earth's water came precisely from these remote regions. But this leads us to the central question that has tormented scientists for decades. After all, how did water reach our planet? Seemingly simple. This question divides the scientific community into competing theories that try to explain how a planet formed in the solar system's habitable zone, hot enough to melt rock, managed to accumulate so much water on its surface. There are two major schools of thought. The first, known as the external origin theory, proposes that Earth's water was delivered after the planet's formation, primarily through impacts from ice-rich comets and asteroids during a tumultuous period of solar history. This idea gained significant popularity, as the violent bombardments of the remote past would represent a perfect mechanism for importing water to a young, arid planet. And these impacts were numerous. During a phase known as the Late Heavy bombardment, approximately 4 billion years ago, Earth was relentlessly struck by objects from the outer regions of the solar system. Imagine the apocalyptic scenario: an incessant rain of space rocks, many larger than entire cities, colliding with Earth's still-forming crust. Each of these catastrophic impacts could have deposited immeasurable volumes of ice, which later melted and became incorporated into the planet's nascent geology. It's almost like a programmed delivery on a cosmic scale. However, the second school, the internal origin theory, argues that water was present from the beginning of planetary formation. According to this view, hydrogen and oxygen would have combined during the very accretion process that formed Earth, with water initially stored in deep minerals or gradually released by primitive volcanoes as the planet cooled. This perspective presents us with a fascinating enigma. Did the water we drink violently fall from the sky or patiently emerge from Earth's depths? A dilemma that has inspired passionate scientific debates and discoveries that challenge our most basic certainties. The hypothesis of comets as the main water carriers to Earth seemed irrefutable, until more precise isotopic analyses began to complicate this narrative. By meticulously examining the composition of hydrogen present in comets, scientists found a significant discrepancy. The proportion of deuterium, a heavy hydrogen isotope, in many comets did not match the chemical signature of water in Earth's oceans. Famous and well-studied comets like Halley's showed deuterium-hydrogen ratios drastically different from those found in Earth's waters, about twice as high. It was like comparing fingerprints and discovering there was no match. This discovery seriously shook the external origin theory, forcing researchers to reconsider their conclusions. However, in 2011, a twist, Comet 103P Hartley 2, originating from the Kuiper Belt, showed an isotopic composition surprisingly similar to Earth's water. Its chemical signature was almost identical to that of our oceans, partially resurrecting the cometary theory. This revealing finding suggested that perhaps not all comets contributed to our water resources, but only specific types from certain regions of the solar system. At the same time, analyses of chondritic meteorites, primitive fragments from the early solar system, showed isotopic compositions remarkably close to Earth's. These rocky asteroids, formed at the same time as our planet, could have been more significant contributors than comets themselves. These contradictory pieces of evidence place us before a complex scenario. We can no longer simply state that water came from space. We need to specify which water, from which space objects, and in what proportion. The challenge lies in identifying exactly which celestial bodies share the same chemical signature as our Earth water, and understanding why some are so similar, while others are completely different. A clue that begins to suggest we might be facing a much more intricate puzzle, possibly a combination of several different cosmic sources. While science's eyes were turned to the sky, seeking answers in comets, revolutionary clues began to emerge from the depths of Earth itself. In 2014, scientists analyzing tiny zircon crystals more than 4.4 billion years old, almost as ancient as the planet itself, found unequivocal indications that Earth already had water even before the late heavy bombardment period. These ancient crystals, true geological time capsules, contained oxygen inclusions with isotopic signatures that could only have formed in the presence of liquid water. This means our planet was already wet in the first 100 million years of its existence, long before the supposed water-bearing comets could have arrived en masse. This discovery dramatically strengthened the internal origin theory, suggesting that water was incorporated into Earth's minerals since the planet's birth. Even more impressive, recent geophysical models indicate that the volume of water present in Earth's mantle may greatly exceed what we see on the surface. Conservative estimates suggest that 2/3 of the planet's total water may be trapped in deep layers, invisible to our eyes. One of the most fascinating indicators of this inner ocean came in 2014, when researchers discovered a rare mineral called ringwoodite in a diamond formed 700 kilometers deep. This microscopic fragment of ringwoodite contained approximately 1% of its mass in water, chemically bound to its crystalline structure. Extrapolating this concentration to the entire Earth's mantle, scientists calculated that there could be a volume of water equivalent to several Atlantic Oceans slowly circulating in Earth's inner layers, not as underground lakes, but as molecules, incorporated into the very mineral structure of mantle rocks. This deep water may have been gradually released to the surface through intense volcanic activity, feeding the primitive oceans and the nascent atmosphere. Imagine Earth as a giant reservoir slowly releasing its aqueous content over billions of years, a planetary version of a cosmic sponge gradually being squeezed by geological pressure. This revolutionary vision leads us to contemplate the possibility that our planet carried its own water supply from the beginning, like a gift wrapped in its original composition. But then, if there is evidence for both internal and external origins, are we facing a false dichotomy? Could it be possible that both theories are partially correct? After decades of controversy, thousands of laboratory analyses, and multiple space missions, the scientific community is beginning to converge on a surprising explanation. Earth's water probably has a mixed origin. Part of it, perhaps a significant amount, was already present in the materials that formed Earth, chemically bound to minerals since the early solar system. Another part arrived later, through impacts from specific asteroids and comets, that, by cosmic chance, had isotopic compositions compatible with the water already present. This hybrid theory, by combining elements from both previous hypotheses, offers the most complete explanation for the available evidence. It reconciles the presence of water in ancient zircons with the isotopic similarities between Earth's water and certain celestial bodies. It also explains why some asteroids have chemical signatures so close to Earth's, probably because they formed in the same region of the protoplanetary disk, sharing similar primordial material. This revelation profoundly transforms our understanding not just of Earth, but of how planetary systems develop. If water is a natural and expected component in the formation of rocky planets, not an anomaly or fortuitous delivery, then it may be accumulating at this very moment in countless forming worlds throughout the galaxy. And where there is water, the possibility of life ceases to be an unlikely coincidence to become an almost inevitable consequence of cosmic chemistry. This new understanding places us before a potentially much more habitable universe than we ever imagined. Water, this extraordinary substance that traversed billions of years and unimaginable distances to reach us, may be the universal link connecting all possible life in the cosmos. A substance that, in its apparent simplicity, carries the complete history of universal evolution, from the first moments after the Big Bang to the thoughts now flowing through your brain as you watch this video. Now that you've delved into the depths of this mystery as ancient as time itself, pause for a moment and consider. How many other seemingly ordinary things, like a simple glass of water, hide epic narratives spanning billions of years and extending to the edges of the observable universe? The true beauty of science isn't just in definitive answers, but in the transformative questions it inspires us to ask. And the question about the origin of Earth's water inevitably leads us to even deeper and more disturbing inquiries. If water is so common in the cosmos, are we really alone in this vast cosmic ocean? Is the life we know an extraordinary statistical exception, or just the first example of a universal pattern we haven't yet been able to detect? Think about the water molecules that at this moment circulate through your blood, hydrate your cells, and enable every biochemical process in your body. Some of them may have traveled through the incandescent core of stars long extinct. Others perhaps arrived on Earth riding an asteroid from a region of the solar system we can barely visualize with our most powerful telescopes, and still others may have emerged from planetary depths, imprisoned for billions of years before finally reaching the surface. And most important of all, what do you do with this knowledge you've just acquired? Does it change how you see the world? Does it increase your interest in nature? Does it enhance your desire to discover more about the mysteries that still exist? If these ideas have sparked your curiosity, subscribe to this channel right now, activate notifications, and come with us to discover the secrets the universe still hides. Because here, knowledge is just the beginning.